Hey class, today's note will be on Gay-Lussac's law. Don't mind the hat. I know you guys are watching this after the break, but I think I'll leave it on for the rest of the note. That's your title. I'll give you a second to copy that down. History. In the late 1700s to early 1800s, French scientist Joseph Gay-Lussac studied several different relationships between the characteristics of gases, but his work on the relationship between gas pressure and temperature is what he's most known for. Using his data, he concluded that the temperature of a certain volume of gas is directly proportional to its pressure. So, for example, if the temperature of a gas drops, then the pressure will drop with it. And he was also able to develop a formula. Now, regarding real-life applications to this, if we know that the volume of a gas is going to increase as its temperature increases, the production and contents of spray paint cans must be fine-tuned so that if the can does heat up, the gas on the inside doesn't expand to the point where it will explode. Now, this can apply to any container that uses compressed gas, such as oxygen tank, etc. Next slide in 3, 2, 1. Gay-Lussac's law. It's the relationship between the pressure and temperature of a fixed volume of gas. There's a formula. P1 and T1 will be your gas pressure and temperature before a change, and P2 and T2 will be your gas pressure and temperature after the change. Now, the temperature must be in Kelvin. As you recall from the first lesson, if we use a temperature scale that has negative values for some of these laws, then in some cases you'll get pressures and volumes that are negative, and we know that's not possible. Now, pressure can be in any unit as long as both sides are in the same unit, otherwise we'll have to convert. And as long as the volume doesn't change, it can be in any unit. Okay, the next two slides will be examples in 3, 2, 1. Example 1. An oxygen tank with a pressure of 4,000 millimeters of mercury at 29.14 degrees Celsius is put into a fridge to be cooled to 17 degrees Celsius. What is the pressure of the oxygen tank if it had time to cool to 17 degrees Celsius? Okay, so in the question, it does tell us the pressure of the oxygen tank before change, 4,000 millimeters of mercury. It also tells us the temperature of the gas before a change, 29.14 degrees Celsius. And it also tells us the temperature after it's put into the fridge is going to be 17 degrees Celsius. That means we do not know pressure 2, and that's what we'll be solving for. Now, before we put this into an equation to solve, if you recall, we have to have temperatures into Kelvin. So to convert, all I'll do is add 23.15 degrees to equal, it'll equal 302.29 Kelvin. 302.29 Kelvin. And I'll also change the other one into Kelvin, just adding 273.15 to get 290.15 Kelvin. Okay, so now that I have both my temperatures into Kelvin, I can now put into the equation and solve. So I'll write my equation, P1 over T1 equals P2 over T2. Then I'll rearrange for the variable I'm solving for, which is P2 will end up being P1 times T2 over temperature 1. Now I can substitute my values in. Pressure 1 said to be 4,000 millimeters of mercury. And temperature 2 we worked out to be 290.15 Kelvin. All over temperature 1, which we figured out to be 302.29 Kelvin. So the kelvins cancel out. I'll plug this all into my calculator and get a value of 3,839.36 millimeters of mercury. And there's your answer. It doesn't tell us to convert the pressure into any other standard form of pressure, so I'll just leave it in millimeters of mercury. And next example in 3, 2, 1. Example 2. The pressure of a gas in a sealed container is measured to be 3.04 bar at 293 Kelvin. If the gas is heated to 309 Kelvin in the same container, what is the new pressure of the gas? Okay, so it tells us the pressure 1, which is 3.04 bar. It also tells us the temperature beforehand, which was 293 Kelvin. And it also tells us what the temperature 2 is going to be, 309 Kelvin. And it is asking us for pressure 2, which is what we'll be solving for. Now, both of the temperatures are in Kelvin, so we don't need to do any conversions. I'll just start with the equation. P1 over T1 equals P2 over T2. I'll rearrange for the variable I'm solving for, which is P2. So that'll be pressure 1 times temperature 2 over temperature 1. Now I'll substitute my values in. P2 equals pressure 1, which is 3.04 bar, or bar, times temperature 2, which is 309 Kelvin, all over temperature 1, which is 293 Kelvin. The kelvins cancel out, and I'll plug that all into my calculator to get an answer of around 3.21 bar. Okay, the question doesn't ask me to put any specific pressure unit, so I'll leave it as bar, and that's it. Thank you for watching Lusac's Law.